All right, welcome back. And today we are going to do a question called arithmetic binary tree. You are given a binary tree representation of an arithmetic expression. In this tree, each leaf is an integer value, and a non-leaf node is one of the four operations: plus, minus, multiplication, division. Write a function that takes this tree and evaluates the expression. All right, so we have an example here. We have a multiplication, and then we have two plus signs here. So essentially what you want to do is you want to add these two together. 3 plus 2, that equals 5, and then 4 plus 5, that equals 9. So then 9, and then we have 5 and 9, and then later on what you want to do is you do 5 multiplied by 9, and that gives you 45. So yeah, so here's a representation of the expression. So essentially it's just parentheses. Whenever you go down the tree, that's basically what's happening. So this question is actually pretty simple. If you know like your fundamentals of understanding recursion, this should be extremely simple. So yeah, so how you begin to do this is you just recurse on the left side and then you recurse on the right side, because the key about recursion is you pretend that everything is already solved. Imagine if you already have the function evaluate solved, then you solve your left, you solve your right, so all you have is a number now, right? And now that you have a number, what do? You're gonna do the multiplication, because that's all that's left to do, right? So let me show you visually how that works. So imagine, first of all, imagine I'm on this node right now. I'm on the root node. Then all I want to do is I want to solve my left part, which is this part, right? And then what I'm going to do is I'm going to solve the left part, and then because I see a multiplication, I'm going to multiply by the right part. So then I'm also going to solve the right part, right? Something like this, right? Conceptually. And then what happens in the solve left? Then we isolate it and we look at here. So it's the same thing we do here. And then when we solve, so imagine now this guy is the root. Imagine these things don't exist, right? So we're not thinking about that. We're just thinking about these two guys. Then it's very simple, because you're going to do the same thing. Solve left, and then you're going to add it, and then you're going to solve right. Now, we all have a base case. The base case is that they're actually leaves, they're numbers. So once they're numbers, that's pretty easy. That's just a 3, and then you also have a 2, right? So once you solve left, that becomes 3, and then you're just gonna add solve right, which is equals to 2, and that gives you 5. So that means solve left, which is this guy, which was here, would end up popping 5 for you. And then you're going to multiply this with whatever this is. So then we're going to do the same thing. This becomes the root. You're going to look at these two numbers. You get 4 plus 5. That gives 9. And then this becomes 9. And then you just multiply by it. So that's pretty much recursion. All you have to do is say solve left, and then look at my node, what it is, and then solve right. And then the base case is if you see a number, then it's just a number, right? Cool. So that's pretty much it. And then now let's talk about the time complexity. So the time complexity of this is O of n. And the reason is because you have to go through all the nodes anyways, and there are n nodes. All right, what about space? So because we do recursion, we have something called a call stack. So because call stack. Okay, so what's the maximum depth you can go? Because we're always, whenever we call recursion, we're going to be here, then we're going to call here, and then we're going to go here, then we're going to pop and go back to this guy, and then go here, and then pop all the way here and go here. So that means the height is the maximum. So the height. So it would be O of log n, because this is a balanced binary tree, and the height is basically log n. All right, cool. Yeah, so that's pretty much it. So let's code it up. So here, like we said, there is a base case. The base case will be if it's just a number. So what we can do is we're gonna deal with all the operations first, and then at the end, if it's just a number, we're just gonna return the value. Cool. So then what we're going to do here is first, if the value is a plus, oh yeah, we already defined the plus minus times right here. So, okay. So because we're Python, it's a little bit easier because value can be a string or a number. So then it'll just do it automatically. But maybe if you're C++, you kind of have to do something different. Okay, anyways. So that we're gonna return. So it's gonna be pretty much the same thing for everything. So you're gonna return evaluate left, which is, like I said, when you solve left, and then you add it because you have the plus here. Evaluate root right. And then that's pretty much it. And then you do that for every other operation. Okay. Okay, so we have minus, we have times, and we have divide. So then we're just gonna match these. Multiplication and division. And then that's pretty much it. So let's see if it runs. All right, perfect. It gives us 45. Imagine if you want to change a number. Let's do something easy like 3. So 3 plus 3, 6. 6 times 9 is 54. Yeah, and we get 54. So that's pretty good. All right, so that's pretty much it for this question. Hope you enjoyed it. See you next time.